So, hello everyone, welcome to lecture 50. So, if you remember from the last class, we were looking at the mechanisms of atomic polarization, so mechanisms of polarization that come from an atomic level. So the dielectric constant which relates to polarizability of which has different mechanisms, and we looked at one of the mechanisms in the last class to look at its frequency response, right. So, and that was orientational dipole moments, taking water as an example, or I also said that it does not need to be water, it can so similar sort of mechanism exists in what are called these relaxer ferroelectrics, where I have all these polar nano regions and they follow this orientational dipole physics. Okay. So, and the physics is nothing but its relaxation, physics of relaxation. When I apply an electric field, the polarizations will take some time to follow the electric field. If I am so if I am doing this at very low frequency, that time does not really matter. You can so polarization almost instantly follows the electric field. If I am doing it at very large frequencies, then polarization just gives up, it does not follow the electric field, the orientational polarization. But if I am doing at this intermediate frequency, where I have the I have defined the time scale of the system or the frequency scale of the system as a relaxation frequency, then at relaxation frequency things become interesting, right. So, the polarization then is out of phase, so goes out of phase with respect to the incident electric field, and so there you start seeing things like so at omega equal to omega naught, or the relaxation frequency, the dissipation is huge, right. So if I see a dispersion in epsilon r, right. So, epsilon r I see a dispersion, which means epsilon r is going down or is changing with frequency, and simultaneously I also see something peaking up in the epsilon I, right. So both of them are happening simultaneously. Again, I am setting up a stage where I am going to say very soon that these are related, but again that has to wait until next class. Okay. Okay. So, now we will scan the frequency region. So, we have gone from the megahertz to, so let us say this is I am going from the megahertz to gigahertz, or so 10 per 10 hertz range, right. So, now I am going to scan the frequency even to much higher ranges. Okay. Below megahertz, what happens? There can be other relaxation phenomena. I have something like space charges, so all these are much slower processes, but all these slower processes just have a relaxation time scale associated with it, right. So, ideally I can have a material with several such relaxation processes, followed by what I am going to talk today, which is called resonance, right. So and then there is going to be one peak here. So, this is epsilon r, and if I look at epsilon I, there is going to be one peak here, one peak here, one peak here, and so on and so forth. Okay. So, and then so followed by what I am going to talk today. So this is what happens up to 10 per 10 hertz or gigahertz or something like that. Okay. All right. So, what happens beyond these frequencies, right. So let us go for the kill. Let us look at how electronic polarizabilities, that those are the easiest to polarize, right. So the atoms, right. So, I said I have an atom with a nucleus, and initially the nuclear center is coinciding with the electronic center of mass. Okay. So, nucleus is in red, electron is in blue, right. So, the nuclear center of mass and electronic center of mass are coinciding, but then so once I start applying an electric field, right. So, this is the electric field. Once I start applying the electric field, the electrons move, the electronic cloud moves down compared to the nucleus, right. So, the nucleus is up, right. So this is the center of mass of electronic cloud, this is the center of mass of nucleus, and I am creating a dipole, right. Yeah. So I am creating a dipole, or I am polarizing this atom, right. So this is the electronic polarizability. If I remove this electric field, this will go back, right. So here I have, it is as if that I have a spring connecting a positive and a negative ion, right. So, electric field is trying to extend the spring and then compress the spring, right. So in some sense this is equivalent to, if I remove the electric field, this will start going back, right. So go to the center of so the centers again merge. Then if I apply an electric field in the opposite direction, so again I have this is negative sorry, I am applying electric field in the opposite direction. So, then the negative charge is going to be here, but the positive charge now with respect to the negative charge cloud is going to go down, right. So, the blue circle is an electron cloud, right. So, this is, that is why instead of moving the nucleus I am just moving the electron cloud, but this is a relative motion. Okay. So, there is you know, so if I leave this, if I apply electric field and leave it, right, apply electric field and then switch it off, then I have a restoring force. Why do I have a restoring force? Because nucleus tries to pull the electrons, and that restoring force is Coulombic force. Between the nucleus and the electron, right. So, this is positive charge, this is negative charge, there is a force in this direction, right. So, that is my restoring force, and because I have this problem is exactly the same as a spring mass system, right. So, where I can extend electrons, so I have a constant, I have a nucleus which is fixed, let us say, and I am moving the electron cloud, you know, so to distances of x naught this way and distances of x naught this way with the applied electric field, right. So, so I can look at the displacement of electrons, because displacement of electron is related to polarization. If nucleus is here and electron center of mass is displaced to a distance x naught, then I have a polarization that is equal to E times x naught, right. So, it is charge times the displacement, that is the dipole moment that I am creating, and that dipole moment is in this direction. Okay. So, so dipole moment is directly related to the x naught, right. So, x naught is the displacement of the electron, right. So, actually minus x naught, because x naught is positive whereas my dipole moment is negative. Okay. So, and that is because the electron charge is negative. Okay. Okay. So, P is directly related to x naught. So, I can follow how x naught is going to change, right, and so this is exactly electron cloud is sloshing around the nucleus, right. So, it is undergoing this simple harmonic motion. So, I can write a spring mass or a you know, equation to describe this. Now, what is spring mass equation? Spring mass equation is you know, so the mx double dot, that is the acceleration that I have, this is the x that I am going to follow, x is the electron displacement, right, plus m gamma x dot okay. So, x double dot is d2 x by dt square, x dot is dx by dt, and you know, plus kx, that is the restoring force, equal to the applied force. The applied force is minus E, right. So, I apply an electric field, and the force on the electron because of an electric field is minus E times capital E. Okay. So, that is the electronic polarizability that I am looking at. Okay. Now, you know, so this is the dissipation term, right. So, that is you know, the force is dependent on x dot, right. So, x dot is the flux, this is the force, right. So, we did all these things earlier, and you know, so this is the equation of a spring mass. What it is called a damped spring mass system. This is the damping term. Okay. Now, how do we so let's assume for starters that gamma equal to 0, that is there is no damping and no external force. If there is no damping and no external force, right, so I stretch a spring and then I release it. Okay. So there is no external force anymore, but the spring is still accelerating and there is a restoring force kx that is equal to 0. And how do I solve? You know, so I'll tell you how to I mean, so I think you already know how to solve these equations, but from this system comes the natural frequency of the system, which is nothing but the resonance frequency, right. So, this will actually, so this is like a pendulum, right. So, or a spring mass, right. So, where the pendulum starts oscillating forever, right, and it oscillates at its natural frequency, right. So, the natural frequency is nothing but the resonance frequency of the pendulum, right. So, because if it goes this way there is a restoring force here, if it goes this way there is a restoring force here, and there is always some sort of an acceleration that is happening. This is the acceleration. Okay. So, this gives rise to some sort of natural frequency, and this natural frequency is nothing but square root of k by m, right. So, for a spring mass system the natural frequency is square root of a by m. Okay. So, this is the resonance frequency or the natural frequency, right, and I do not need to, in this course I will not go into what is resonance etcetera. The assumption is, you would have studied about resonance in one of your high school, right. So, earlier classes you would have definitely studied resonance. Now, I force I look at so what happens when I apply this, right. So, mx double dot plus kx, I am still gamma equal to 0 equal to I am going to force the oscillation, and that is equal to minus E E. Okay. Now, how am I forcing the oscillation? I am going to apply E as E naught e power minus I omega t. Okay. So, then I have this equation mx double dot plus kx equal to minus E naught e power minus I omega t. How do you solve these equations? You assume that x is actually going to be driven at the same frequency as the electric field. So, I am going to assume the solution to be x equal to x naught. I am just doing it fast because these are standard things. You can, even if not through this course, you can find these sort of derivations on YouTube, but for completeness I am just doing it here. So, I am going to assume a solution where x equal to x naught e power minus omega t, and so mx double dot will have an m omega square. I think I times I will come out, minus I times minus I will come out. So, that is a minus m I omega square e power minus I omega t plus k x, x is just x naught, sorry, there is an x naught also here, right, k x naught e power minus I omega t. So, the idea is to find what x naught is, right. So, that the solution would involve finding what x naught is equal to minus E naught e power minus I omega t. Okay. So, now I know that k by m is nothing but my omega r square. So, I am going to use that fact here. So, I am going to divide this entire equation by m. So, what I have is omega square x naught plus k x naught by m equal to minus E by m E naught, right. So, all the e power minus I omega t's go away, and that implies so I have an omega square plus omega r square. So, x naught times omega, sorry, there is a minus here, right. So, omega r square minus omega square equal to minus E by m E naught, okay, or x naught equal to E by minus E by m, let us just keep it as minus E by m E naught times omega r square minus omega square, right. So, this is this is the amplitude of oscillation, right. So, amplitude of oscillation is a function of frequency, x naught is a function of frequency, that is what you get from here, right. Now, x naught I said is related to the polarization, right. So, whether I look at the displacement of electron away from the center or whether I look at the polarization, it is one and the same, the polarizability rather, not polarization, but polarizability of the electrons. Okay. So, now let us try to plot this. Okay. Now, as a function of omega, omega is changing, I have x naught, or so I am going to plot what minus x naught is. X naught is equal to, so we have this function omega r square minus omega square, I just omega r square minus omega square and minus E naught, right. So, minus x naught is just this, right. So, let me plot what minus x naught is. Okay. At omega less than omega r, right. So, this is a positive quantity, correct, and so it will start at some quantity at omega equal to 0, right. So, what happens at omega equal to 0, minus x naught will start at some quantity, and then as omega approaches omega r, right. So, from omega is approaching omega r, from so from the left side, right. So, this is a positive quantity, but it keeps increasing in magnitude and it just goes to infinity. Okay. Now, as omega is greater than omega r, so at infinity this is 0, that is okay, but as omega approaches omega r, this again goes like this, right. So, this is how this will look like. Okay. Now, all right. So, minus x naught is the same as the polarizability or the susceptibility, right. So, polarizability and polarizability is related to susceptibility, right. Now, susceptibility, electronic susceptibility or electronic the susceptibility coming or susceptibility or dielectric constant coming from electronic polarizabilities. Okay. They have some value here, they are going to 0 at infinity, that is true, right. So, we said it starts with some value, it goes it goes to a low value or 0 at infinity, that means this mechanism gave up here. Here mechanism persists or in phase, right. So, polarization is in phase with the electric field, but how does it go from here to here? Oh boy, it takes a bad turn, right. So, it is not continuous anymore, it goes up to infinity, it goes down to infinity, there is a sudden discontinuity and then comes up, right. So, no way, I mean I cannot just extrapolate this from here to here, right. So, I cannot just extrapolate, so I cannot just do this and then say, oh, what, this is how polarization goes to 0, this is how susceptibility goes to 0, that is not what I can do, right. So, when I solve this spring mass system, what I get are these discontinuities, right. So, okay, so let me erase this, right. So, I would never have predicted this if I did not solve it, okay. So, let me just draw this, okay. So, I would have never predicted it if I did not solve it, right, okay, good. So, that is fine. So, this is a non-dissipative system, right. Now, let us put in some dissipation, right. So, into the spring mass system, let us put in some dissipation. Or friction, gamma, that is electron can go up and come down, but the lattice or the way electron is getting polarized, there is some friction to it, right. So, it is like there is some friction to the spring mass system, so this electron cloud is sloshing up and down the nucleus, right. So, at a very high frequency, but it is going through a viscous medium, right. So, there is it's dissipating energy, right. So, in the form of friction. Okay. So, then if I put in friction, right. So, I go back and modify my equation. So, I go back to the master equation which is with friction. So, that is this, right. So, mx double dot plus m gamma x dot plus kx equal to minus e naught, right, e power minus I omega t, but now I can again assume that x equal to x naught e power minus I omega t, but this time I am okay with having x naught as not a completely real valued function, but x naught can be complex, right. So, if x naught is complex, x naught is complex, then there can be some phase that gets added to the omega t, right. So, it is not exactly, x is not exactly in phase with E is oscillate, there is, let us say the phase of E is 0, then there will be some phase difference for x, right. So, compared to E. Okay. So, to incorporate the phase difference, I allow for x naught to go imaginary, right. So, or not imaginary, but yeah. So, x naught can be a complex function. Okay. All right. So, now if x naught can be a complex function, sorry, let me just I will just write down the solution. So, x naught, the solution for this is going to be minus e naught divided by m omega r square minus omega square. This is the general solution I have, but there will be this gamma term, right. So, omega r. which is going to give this, right. So, this is a typical spring mass system, right. So, if you come to ISC for interviews, if you take an interview for PhD, it is imperative that everyone solves a spring mass system before, right. So, these are the sort of questions that we ask you in interviews, right. So, what is a spring mass system, what is the solution for that, right. So, I will not do it in this course, but you know, so this is something that you should be aware of, okay. You know, so again I am giving you interview questions in this course, okay. So, if you are interested to come and join us as PhD students, you know, so this is one of the questions that you may want to prepare for, all right. Okay. So, you know, so this is the solution, this is the generic solution, and here I can divide this into a real part and an imaginary part, okay. Okay. So, if I do that, yeah, so this is, you know, so again I can do this trick of x naught being minus E naught times m omega r square minus omega square plus I omega r, right. So, I bring out all the, you know, complex nature to the numerator, and in the denominator I just make it a nice real number, right. So, omega r square minus omega square whole square plus omega r square. So, that is the solution, and you know, here if we plot, you know, so earlier we said if I plot minus x naught versus omega, you know, at omega equal to omega r, this thing actually diverges, right, and you know, this is what happens, right. But now, right, so now I am going to plot two different functions, right. So, one is so this is non-dissipative case, or gamma equal to 0, okay. So, now I am going to do the dissipative case where minus x naught versus omega. The real part is the non-dissipative part, right. So, real part of polarization that does not dissipate, that is going to go somewhat similar, but it is not going to go to infinity, it is going to come down, go like this and then go to 0, okay. So, what people call, I mean the mechanical engineers, especially people who do MEMS, right. So, they call this as a resonance peak. This is a resonance phenomena, by the way, I am looking at the natural frequency of the system, right. So, this is called the resonance peak and this is called the anti-resonance peak. If you are doing MEMS based measurements, you can measure these frequencies for, you know, something like ionic polarizations, especially if they are low gigahertz, you can actually do these resonance measurements and then measure these frequencies, right. So, that is what some of my colleagues in my department do. They are MEMS experts, but they measure things at a few tenths of gigahertz and they can actually measure these frequencies, okay. So, this is resonance, this is what is called anti-resonance peak, okay. Then you know, so what about, you know, so okay, minus x naught, so okay, so I will just say x naught of real is in black. Now, there is an x naught imaginary part that tells me the loss, or that tells me the resistance component or the conductance component that dissipates energy, right. Now, that, you know, so you can actually see from this formula, that is omega r divided by this entire thing, right, that will give you a peak at omega r again. So, that will peak at omega r, and you know, it is the same shape as what we had for relaxation, right. So, this is the you know, the peak of minus x naught imaginary part, okay. So, or the peak of dissipation happens at omega r, happens at the resonance frequency, right. So, we assume that okay, the system is vibrating, you know, so at the same frequency as the, you know, so at its natural frequency, I am driving the system to vibrate at its natural frequency, but the thing, you know, so there should be large amplitude, right. So, this is how bridges collapse, right. So, bridges are you know, so soldiers march on bridge and this bridge catches its natural frequency and then it starts vibrating, the amplitude of vibration just increases, right, but that is okay. Amplitude can increase, that is okay, but along with amplitude of vibration, this sort of dumps a lot of energy into the surroundings, right. So, this dissipates a lot of energy, it just heats up, right. So, the amplitude is increasing against the friction, right. So, in a very heavily viscous medium, right. So, if there is huge wind that is flowing towards you and then you start cycling really fast, right, the friction force is huge. I am actually dissipating a lot of energy, right. So, I really lose a lot of weight if I do that, right. So, on a very windy day or a stormy day, I start cycling really fast, right. So, that is a recipe of weight loss, for example, right. So, if you want to lose weight, right. So, I have to spend a lot of energy, right. So, I have to dissipate my energy. This is exactly what is happening. I am setting the system into resonance. So, the electrons are sloshing around sort of vigorously, but they are sloshing around in a viscous medium. So, there is some drag force, and every time they go this way or that way, they just give away some of the energy to the system, and this energy is taken by phonons, or it is used as heating the material, right. So there is a peak that exactly so the peak happens at the resonance frequency at omega r, right. So, the amplitudes increase slightly away from the resonance frequency. If you see the resonance peak and anti-resonance peak, they are the amplitudes that are increasing slightly away from the resonance frequency, but the dissipation is maximum at the resonance frequency. Okay. So this is the solution of the spring mass system, and this is the resonance phenomena that also happens for my polarization, right. So now if I complete the diagram of epsilon r or susceptibility, it does not matter, as a function of omega, right. So, initially there is going to be some relaxation phenomena up to until gigahertz. Okay, so let me actually draw it properly. Right, epsilon r, okay, so epsilon r real part, right. Initially there are going to be a few relaxation phenomena, right. So, space charge, something like orientation or PNRs, relaxation, space charge. So, this relaxation corresponds to space charge, this relaxation corresponds to PNRs, right, and so on and so forth. Then I enter the regime of terahertz, right. So this is all the way up to a few gigahertz, right, or in materials it can be less than gigahertz, that is okay, right. So then I enter the regime of terahertz, and in terahertz there is going to be ionic polarization. The only thing that is dominating here is ionic plus electronic polarizabilities, right, and the way that will go down, right. So the way ionic polarizability is dying is like a warrior, right, it resonates first, right. So it goes up, the amplitude of dielectric constant actually goes up, there is huge amount of polarizability here, it's setting, your system is set into resonance, right. So and then so it decreases, right. So it decreases above this value is less than this value, okay, and eventually there is going to be electronic, so this is going to happen in terahertz, and eventually there is going to be electronic resonances, and electronic resonances are also going to happen about this, right. So they are also going to die fighting, and so this is, here I have only electronic and here I have nothing, right. So here I have nothing. When I have no more polarization mechanisms, right. So this is some UV or deep UV or something like that, right, and when I have nothing, then that is X-rays, right. No polarizability mechanisms. I can apply whatever X-rays to my material, material does not get polarized. X-rays diffract, that is a different issue, right. So the wavelength is so small that they see atoms not as, it does not see the material as a homogeneous material, it sees material as set of different atoms, right. So that is a different issue with X-rays, but let us ignore that fact for a while. So you cannot use what are called mean field theories when you are actually looking at the epsilons or the refractive indices, the dielectric constants or refractive indices when you are using X-rays. Okay. So that is a caveat, I am not going to go into details about that, but just let us assume that at X-ray frequencies there are no polarizing mechanisms, right. Just like then the material behaves like vacuum. At X-ray frequencies, right. So there are no polarizability mechanisms, electrons cannot polarize, right, ions cannot polarize, even in vacuum, right. So if I have a capacitor, right, and this is just vacuum, these are parallel plates, this is metal 1, this is metal 2, and I apply an electric field, what I end up measuring is I end up measuring epsilon naught, right. So this is the vacuum dielectric constant, or the dielectric permittivity, which is epsilon r, equal to 1, or susceptibility equal to 0, right. So, vacuum is not susceptible for any sort of polarization, vacuum is the hardest dielectric material ever, right. So, at X-ray frequencies my epsilon r actually goes to 1, right, or it is actually slightly less than 1, not exactly 1, slightly less than 1 because of the caveat that I told you, I shared with you just now, which is that the X-ray wavelengths are comparable to the atomic sizes, right. And so, now when X-rays go and impinge your material at visible frequencies, right. So, when I shine light into my material, the lambda of light is about 500 nanometers and the atomic sizes are still angstrom sizes. So, this is 5 angstroms. So, in 1 lambda I have about 500 nanometers divided by 0.5 nanometers, that is about 1000 atoms, right. So, there is some sort of, I am seeing so when I measure properties using light, susceptibility, or it turns out to be, I measure the refractive index using light, I can average over actually 1000 by 1000 by 1000, right. So, if I take the volume, right, so it is 1000 by 1000 by 1000, right. Right. So, I can average over some 10 power 9 atoms, right. So, that is a good statistics, right, to find the property, right. So, then my property actually belongs to at least 10 power 9 atoms, right. So, my property is derived from at least 10 power 9 atoms. My global property, which is the property of the material, so belongs to 10 power so is extracted, not belongs to, is extracted from at least 10 power 9 atoms as an average response, or not average, ensemble response of 10 power 9 atoms. But if I shine X-rays, for example, the wavelength of X-rays is 0.5 nano angstroms, that is less than my atom to atom distance. So, the way X-rays see my sample, material rather, as totally inhomogeneous material, right. They see all the atomic potentials I have, right. So, this is one atom, this is second atom, this is third atom, right. So, they see every individual atom separately, they do not see all of them together, right. So, they do not see that as one material, they see them as 10 power 9 different materials, right. So, X-rays see 500 nanometer region as 10 power 9 different materials. So, they see every individual atom, right. As a result, some of the extracting what is epsilon, which is a global property, this is an ensemble property. At X-ray wavelengths, needs more thought. You cannot just ensemble average so this inhomogeneous material, right. So, needs more thought and as a result epsilon r so although if we just do not think about all these things, we say epsilon r equal to 1 at X-ray frequencies, but epsilon r tends to be slightly less than 1 for many materials at X-ray frequencies, right. So, you can still define an epsilon r, but so you have to consider that so X-rays are beyond what is called so you cannot use this ensemble averaging approach, or that is what is called the mean field approach. Okay. So, So anyway, so that's a detail, but that's okay. So you cannot really use the mean field approach to describe materials at X-ray wavelengths. Okay. So but in any case, so I don't, if I don't really worry too much about what is happening with respect to X-rays up to UV, right. So I have, this is going to be my dielectric dispersion, right. So this is the dielectric dispersion. Now what happens to the imaginary part of epsilon, right? Imaginary part will have one peak here, this is another relaxation frequency. So this will have peak, this will have a peak, right. So this will have another peak, that is my third relaxation. Then so I have the ionic, this is a resonance, right. So until here are relaxations, right. So the peaks are coming because there are some sort of relaxations that are happening, but here this is these are all resonance phenomena, right. So and then there is going to be one more peak here. So these are all resonance, right. So what is the difference? At resonance frequency the system is the polarizability is going to fight and die, right. In relaxation it just gives up, it just naturally so the epsilon r just relaxes very casually, right. So it just gives up, right. So all right, so I am a government in power, I am losing power, so fine, I do not fight for it, right. But so if I am a resonance phenomena, then I am a government in power. If I am losing power, I fight like hell, right. So I tell the people that do not vote for the other person, vote for me, whatever. So that is the analogy, right. So so I up my I up my activity in terms of the oscillation that I see, but as a result I am spending so much of resources, so much of energy, and I am dissipating so much of heat, right. So there is so much of vitriol when I am actually campaigning for my election, right. And eventually, okay, if I lose, right. So but I tried, right. So they lose eventually, right. So the ionic polarization just gives up at much higher it's more forced conditions, right. So I have to oscillate the electric field really fast, then it's like, okay, it's impossible, I have to run in conjunction with the Vande Bharat train, and that's not possible, right. So especially when it is going really fast, okay. So so this is the epsilon dispersion, okay. Now just to extend this, any property, right. So any thermodynamic property will have a similar dispersion, right. There are going to be relaxation mechanisms, there are going to be resonance mechanisms, right. On if I coarse grain it, and if I don't exactly consider how the resonance is coming from, it's not electronic polarizability, it's not ionic polarizability, but some other mechanism, right. So if I'm considering my D33, or if I'm considering my elasticity, right. So the stiffness, right. So there will be some relaxations, there will be some resonances, right. So all these are going to depend on the property that I am looking at, atomistic scale dynamics that I am looking at, but in general the relaxations and resonances are how properties die down with frequency, right. So let me just write that, because that's a statement that looks like a statement of war, right. So properties die down, let's thermodynamic properties with frequency through either relaxation or resonance mechanisms. Okay, fine. So with that, I think that's a good time to end this lecture. In the next lecture, I would argue that so whenever so somehow let's observe this fact and end this lecture. Okay. So somehow when the real part of dielectric constant is going down, or so there is some sort of huge fluctuation, that is when the imaginary part is peaking, right. The imaginary part seems to know what the real part is doing, right. So the imaginary part seem to know what the real parts are doing, which are dissipative of thermodynamic quantities, right. So I take a thermodynamic property, okay. So let me qualify this, right. So I take a thermodynamic property which is supposed to be energy storing, but make it complex, right. So, I take a property P and P is actually PR plus IPI. Then I am saying that PR is the real thermodynamic property, PR is the energy storing property, and Pi somehow I sneaked in the the dissipative property, and we will actually show that PR and Pi will know each other, right. So, the dissipative property, dissipative nature, right. So, and then that makes sense that I define this as a complex quantity, otherwise if PR and Pi do not know about each other, then there is no point putting them together, right. So, if they are married together, they should know everything about each other, right. So, imaginary parts and the real part of what I still call a thermodynamic property, right. So, I start with susceptibility. In the second part of the course, I said susceptibility is a thermodynamic property, right. It comes out of thermodynamics. I have added more complexity. I sneaked in dissipation. I said okay, it does not make sense to look at thermodynamic properties only as energy storing properties. For all mathematical convenience, I will just add in a complex term there, and I will put in the corresponding dissipation. If I have epsilon, I put in the corresponding conductance, right. So, as the imaginary part, right. So, imaginary part of a real thermodynamic property, right, is dissipative in nature, right. So, that is how I still call it a thermodynamic property, although there is dissipation here, right. So, I am evolving with frequency, I am evolving my definition of a thermodynamic property. It is a complex property, and complex property, the real part is the real energy storing part and the imaginary part is the dissipative part. So, I have evolved my definition compared to what I did in the static case in part 2. Okay. So, however, these people, the real part of the property and the imaginary part of the property, this is the energy storage part, right. These are actually married to each other, and it is a working marriage. They know about each other, right. Now, how exactly do they know about each other? And that is what we saw here, right. Somehow when something happens to the real part, the imaginary part seems to know about it. Something happens, the real part is relaxing, the imaginary part knows about it. The real part undergoes huge fluctuations, the imaginary part knows about it, right. So, something is happening in the frequency spectrum, the real part and imaginary part seem to know each other, and we will actually see what this marriage is, right. So, and how the real part knows about the imaginary part and the imaginary part knows about the real part in the next class. Okay. So, with that, let us conclude this class, and next class we will start with what are called how these properties are really related to each other. Okay. Thank you very much.